This video covers section 6.2, surfaces of terrestrial planets are affected by the processes in the interior. We can learn a lot about the individual planets by comparing them. This approach is called comparative planetology. The same physical processes operate on all the planets, but it makes sense to compare them to Earth, since that is the planet for which we have the most observations. There are four processes we will focus on: impact cratering from asteroids and debris, tectonism, which is geological activity such as earthquakes and the motion of crustal plates, volcanism, erosion, which is the smoothing by processing such as weathering or water. These processes are stronger or weaker or even absent on different planets. For example, we would expect planets lacking atmospheres would experience less erosion since there would be no wind or water causing the weathering. The smallest two terrestrial worlds, Moon and Mercury, have no atmosphere, and the other three have atmospheres ranging from very thin on Mars to extremely dense on Venus. In particular, tectonism and volcanism are determined by conditions in the interior of the planet. The focus of this video is to understand the structure and interior processes of a terrestrial planet. Most of the information about the structure of the Earth comes from earthquakes. Earthquakes are measured with a seismometer or seismograph, which record the amount of ground motion that is occurring. This movement is Earth's crust, and it's associated with the massive destruction and tsunamis that can occur. There are three types of earthquakes: P waves, which are longitudinal earthquakes that travel through the interior of the Earth, and usually the first wave to be recorded by the seismograph. They're usually the sound waves that travel through solids, liquids, or gases. S waves are transverse earthquake waves that travel through the interior of the Earth and usually are the second wave to reach a seismograph, and they only travel through solids. The third type of seismic signal are the surface waves, the L waves, and these travel along the Earth's surface on the layer boundaries in the Earth. Surface waves are the slowest waves, but the ones that do the damage in the large earthquakes. Seismic signals can bounce off boundaries in the Earth. Each leg of a signal describes its history up to that point. Seismic waves recorded at increasing distances from an earthquake indicate that seismic velocities gradually increase with depth in the mantle, and we don't see any S waves passing through the core. In 1914, Gutenberg showed the existence of a molten core beginning at the depth of around 2,900 kilometers. At a depth of 5,050 kilometers, the Earth has a solid inner core. The P and S waves travel at different velocities, and the difference in their arrival time at different locations is an indicator of their distance. The earthquake location can be found by triangulation of those distances. Seismic signals can bounce off the boundaries in the Earth. Each leg of a signal describes its history up to that point. Seismic waves recorded at increasing distances from an earthquake indicate that seismic velocities gradually increase with depth in the mantle. We don't see any S waves passing through the core. We can't directly measure the interior of the Earth. The deepest holes drilled are about 12 kilometers beneath the surface, and this is only a small fraction of the 6,378 kilometer radius. We model the Earth's interior by studying earthquakes. Earthquakes produce seismic waves that travel differently through different materials, which gives an indication of the density of the material. The Earth's structure consists of a crust, a mantle, an outer core, and an inner core. Differentiation in the early Earth is such that the dense matters sink and the low density materials rise. The process of differentiation, because of the radial symmetry of gravity, produces a layered interior. Earth is somewhat of an onion. The crust is the outermost layer, which includes a lithosphere. The crust consists of two types of rocks. The continents are formed from low-density rocks such as silica and granite. The ocean basins are formed from denser iron-rich basaltic rocks produced by volcanoes. The thick mantle forms most of the volume of the Earth, and is situated between the crust and the core. The core is made of very dense materials such as iron and nickel. The outer core is liquid nickel and iron. The layers of the Earth were produced by the process of differentiation. During the accretion phase, the impacts heated Earth. In addition, a lot of heat was produced by radioactive elements. The rate is lower nowadays since some of the elements have decayed. Both of these effects would have produced so much heat that the Earth was molten throughout. In a molten Earth, heavy elements would sink to form the core, while the lighter elements would rise to form the crust. The Moon formed by accretion, as did the other terrestrial planets, but many features on the Moon point to a formation process known as the giant impactor hypothesis. Early in its history, Earth probably collided and merged with a very large body about the size of Mars. Much material was scattered into orbit around the Earth as a result of the collision. The material accreted to form the Moon. The best evidence for this is that of the composition of the Moon is like the Earth's crust. The crust and the inner core have different compositions because of differentiation. Heavy elements would sink and light elements would rise in a molten Earth. The Moon's Maria and ancient lava flows from subsequent large impacts. These flows filled the basins made by the impacts. By then, the accretion rate was so much lower, so the Maria have fewer craters than the highlands. An important consequence of gravity is the production of tides. This phenomenon is most pronounced when two objects are reasonably close together. We can see how tides work by considering Earth and the Moon. Since they are not point masses, parts of the Earth are in fact at different distances from the Moon. The essential point is that one side of the Earth is closer to the Moon than the other side is. Gravity varies with distance and is stronger when two objects are closer. The force of gravity between Earth and the Moon is stronger on part of the Earth that is closest to the Moon. As a result, the Earth experiences forces that stretch it along the line connecting the Earth to the Moon, and it is easy to realize that there will be a tidal bulge on one side, but not so easy to note that there will be one on the other side as well. The Moon pulls one part of the Earth closest to the most and part farthest from the least, and the middle an intermediate amount. In the sense, the part farthest from the Moon is left behind, creating a bulge, not because it is pulled, but because the rest of the Earth is being pulled from it. These are the tides, more properly called tidal forces, that operate on Earth. Reversing the argument shows that there are also tidal forces operating to stretch and pull on the Moon. The oceans respond to the tidal forces more than the solid Earth does. This produces a noticeable rise and fall of the level of the oceans about twice a day. The oceans bulge out along direction of the tidal stretching. The ocean level is lowered on a line perpendicular to that. Think of a spherical Earth surrounded by an oval ocean. The bulge is not large, only a meter or two out of the diameter of 11,000 kilometers. The bulge is always aimed toward the Moon, but not always pointed exactly at it. Earth rotates every 24 hours, and each location on Earth passes through the tidal bulge about twice a day. Thus, there are two high tides and there are also two low tides every day. The interval between successive high tides is about 12.5 hours. The Sun also exerts tidal forces on the Earth. These are called solar tides, while the ones from the moons are called lunar tides. The tides from the Sun are about 1/3 as strong as those from the Moon. Land masses of Earth respond to the tidal forces as well. Solid bodies will not change as much as liquid ones, but they will still deform and stretch. This stretching also has an important consequence, friction. Just like other situations, such as rubbing your hands together, friction generates heat. Stronger tidal forces generate more friction, resulting in more heating. The semi-diurnal amplitude of terrestrial tides can reach about 55 centimeters at the equator. The Moon also has a ground or body tide. Body tides in planets and moons, as well as binary stars and binary asteroids, play a key role in long-term dynamics of planetary systems. For example, it is due to body tides in the moon that it is captured into a 1-to-1 spin orbit resonance and is always showing us one side. Owing to the body tides in it, Mercury is trapped into a 3-to-2 spin orbit resonance with the Sun. Tidal forces produce the energy for geological activity of moons around planets such as Jupiter. The evolution of the outer terrestrial planets would be similar to that of Earth, except for the differences due to each planet's size. Currently, all the planets have hot interiors but cool surfaces. All would have been molten during their formation and would have experienced differentiation. Elements that are radioactive will also provide heat as they decay. Smaller planets have more surface area compared to their volume, and as a result, small planets lose their internal heat faster. An analogy is the rate at which food cools. Large potatoes cool more slowly than do small ones. Smaller planets also have less radioactive material in them to produce internal heat. This happens simply because they are smaller, so they can't have more. They probably don't have a smaller concentration of radioactive material. These and other effects allow planetary physicists to construct models of other terrestrial planets. Earth's magnetic field is like that which would be produced by a large bar magnet at the center of the Earth. Note that the north magnetic pole of Earth is actually a south pole and vice versa when compared to a bar magnet. The motion of the Earth's interior most likely contributes to a magnetic field, but that means by which is produced is not fully understood. However, it is most likely due to charged particles in the liquid outer core that is moving as Earth is rotating. Charged particles moving in circles create currents, and electrical currents, create magnetic fields. The magnetism in rocks of the mid-Atlantic ridge show that the Earth's magnetic field reverses directionally quasi-periodically. The north and south poles of the bar magnet flip their orientation from time to time. On terrestrial planets, only Earth and Mercury have significant magnetic fields. Mars has a weak field and Venus has none. Whatever mechanism produces magnetic fields must explain this difference. It is also known that the moon is no longer having a magnetic field, though it did at one point, as evidenced by rocks that have been studied. Earth and Mercury are the only terrestrial planets with substantial magnetic field. Mars has a very weak magnetic field, and Venus has no magnetic field, likely due to its extremely slow rotation rate.